The premise of this presentation is that black holes are invisible quantum mechanical objects that interact with our universe only through gravity, gravity being an undefined property of space. As for the photographs we have, the pictures of Sagittarius A star and the black hole at M8 87, they don't really show the black hole itself. What they show is the extreme frame dragging caused by the supernovae implosion, not explosion. This presentation tries to cover a very complex topic, which makes it a bit extensive. So I created an index of various topics. So let's say you're familiar with the conventional perspective, you can skip the first 14 slides. If you're interested in a black hole's gravitational field and time dilation, and I'm comparing it to the Earth, you can skip to slide 30, etc. Pick and choose the topic that interests you, or if you have the time and inclination, you can watch the entire presentation. Now, Earth's escape velocity is almost 25,000 miles per hour, meaning anything flying upwards at that speed can never return back to Earth. Black holes are astronomical objects with an escape velocity equal to the speed of light, meaning not even light from an imaginary flashlight pointed upwards from a black hole can escape a black hole's gravity. Black holes can form in a number of ways, but right now they usually result from supernova explosions. See, a star has two main components: the outer part, which is basically storage for lighter elements, and the core, the furnace capable of fusing lighter elements into heavier ones, a process that releases heat. Within the star, gravity and heat are at an impasse. Gravity tries to shrink the star while heat tries to expand it. The balance between these two factors allows the star to exist in terms of size and energy creation. As an example, our sun fuses hydrogen into helium in its core, thereby producing heat. This reaction depletes hydrogen and accumulates helium. Eventually, the sun starts fusing helium, which generates additional heat. This additional heat overcomes gravity, which expands the sun into a red giant and blows away the sun's outer layer, forming what's known as a planetary nebula. Left without fuel or pressure, the exposed core very slowly cools as a white dwarf. Larger stars follow a different path. Because of their stronger gravity, these stars can also fuse heavier elements such as carbon, neon, and oxygen. The last reaction that can produce heat is the fusing of oxygen into silicon. Unfortunately, this reaction produces very little heat, meaning the core temperature drops, and without heat to support the star, gravity shrinks the star. This shrinking increases pressure on the core, which raises the core temperature, and the core now begins fusing silicon into iron and nickel. The problem here is that fusing silicon into iron and nickel is an endothermic reaction. It absorbs heat. This rapidly cools and shrinks the core, leading to an explosion we call a supernova. This explosion happens in the core and propels most of the star's matter outward. The remaining mass gets compressed into what's called the singularity, and the gravity from the singularity remains. What was a star is now a black hole, a gravitational well, and from the surface or the edge of this black hole, nothing, not even light, can possibly escape. In this scenario, all the remaining mass from the supernova is concentrated into the singularity. So as we approach this point from outside, the acceleration of gravity exponentially increases, and at the black hole center, gravity becomes infinite. At the point, the shell, the edge, where the escape velocity from the black hole equals the speed of light, that's called the event horizon. Because of the strong gravitational field and what can be considered the time factor, nothing that crosses into the event horizon can ever leave a black hole. Even light that gets too close to a black hole gets trapped outside the event horizon in what's called the photon sphere and follows the bent spacetime, thereby circling the black hole. We call this effect gravitational bending. In this picture, light from behind the black hole follows the bent spacetime, and we see it as if light itself is bent to the top and bottom of the black hole. Now, according to special relativity, time can be stretched like a rubber band, and the strong gravity around the black hole can stretch time, or dilate or slow down time. At the event horizon, gravity stops time. An unlucky astronaut that's falling toward a black hole perceives time differently from someone who's far from the black hole itself. To the astronaut, time elapses normally. His clock will take 60 minutes per hour. But a distant observer watching through a powerful telescope will see the astronaut clock slow down. That's called time dilation, and eventually freeze at the event horizon. Or maybe the clock will seem to slowly fade away since light gets stretched into the invisible part of the spectrum. Either way, eventually light from the clock can't escape the black hole's gravity. There are a few problems with the conventional explanation, and one of them is that black holes have mass. We don't really have a good definition for mass. In high school, mass was defined as the amount of matter in an object, and matter has anything that has mass, kind of like a circular reasoning. A is B because B is A. In college, I was told that according to Einstein, mass is a form of energy, but that requires a better definition for energy. To say that energy is mass, it's circular again. Take a look at this video. Another problem is gravity. We were told that mass creates a gravitational field, and that's what we call gravity. But if all matter is destroyed by the supernova, isn't mass also destroyed since mass is the amount of matter in an object? Again, take a look at this video. And without mass or matter, how do black holes create gravity? Does this imply that gravity existence is independent of mass? The concept of gravity as bent spacetime suffers from the same disease. With the destruction of matter and mass, shouldn't spacetime snap back to smooth, thereby destroying gravity? Again, take a look at this video. Time to look at an alternate way of creating a black hole. A large star, one that ranges to 10 to 20 solar masses, starts fusing silicon, creating iron and nickel. That's an endothermic reaction, and heat is absorbed, it's removed. This cools the core, and gravity collapses the star's outer layer onto the core. The star's outer layer still contains lighter elements, such as hydrogen and helium, and these elements are the ones that come crashing down onto the core. This injection of light elements onto the outer core restarts fusion in the outer core, which increases the temperature of the core surface. This increasing temperature increases the pressure on the core, which accelerates the fusing of iron and nickel. This fusing further cools and shrinks the core, which accelerates the collapse, basically a feedback process. This heating of the core surface becomes an explosion. The explosion propels the star's outer layer, and only the outer layer, outward. And that's what we call the supernova. Below the core surface, the explosion compresses the electrons and protons, turning them into neutrons. This creates a neutron star, a type of matter we don't encounter on the Earth itself. In a larger star, one with a mass that's greater than 20 solar masses, the compression from the supernova implosion crushes the core past what's called the neutron degeneracy pressure point, the point where neutrons can withstand the pressure, and they're forced closer than they can survive as neutrons. Note, the mass of the entire core is being compressed. In other words, a supernova core with a minimum mass of 3 to 4 solar masses forms a black hole that has the same mass as the star's core that went supernova. As the compression wave from the implosion races toward the core center, it destroys all the matter it encounters. But the destruction of matter doesn't destroy mass. The compression returns matter to its original form as what I visualize as very dense dark matter, while releasing the energy that was bound in matter when matter was created. Again, only matter is destroyed, mass remains. Again, take a look at the video for more details. When the compression from the supernova reaches the core center, it rebounds, a rebound that's similar to the Big Bang. At the rebounding moment, the supernova core has become a black hole, and inside it, our physical laws break down. Our concept of gravity, entropy, time, etc., they become meaningless. Space itself inside a black hole is different. It is denser because all baryonic matter reverted back to dark matter, and now it's in a smaller volume. The dark matter particles that make up the black hole are just like neutrinos. There's little to no attractive or repulsive force between them. That's why I believe that the density of dark matter inside a black hole is extremely high. In other words, black holes are places where space density is immeasurably high, but uniform. There's no singularity. In previous videos, I defined dark matter as the fabric of space and energy as a disturbance, a compression in this fabric. If the compression created by energy in the dark matter is in the proper range, that energy gets bound to dark matter and creates two particles with mass being space itself. If the compression has the wrong energy, particles can still be created, but they are unstable. They have a half-life. The half-life depends how far they are from what I call the proper range, but I stray. In this reasoning, mass is just compressed space, and matter is compressed space and energy bound together. So, as an example, in a matter-antimatter reaction, mass is destroyed, E equals mc squared, energy is released, and I expect dark matter particles to be freed, which would vibrate space. These vibrations could actually be measured with the LIGO interferometer. We could just explode a thermonuclear device in space above the interferometer and watch the interference pattern in the device. Easier said than done. So why am I going into energy, dark matter, mass, matter, and antimatter reaction in this section? Well, the formation of a black hole involves three sources of energy. The energy in the star's core before the supernova event, the energy from the compression of the supernova implosion, and the energy from the matter reverting back to dark matter. When all this energy is locked into a space that's extremely dense, what do you get? Well, the high density dark matter and high energy combine to form one particle, which we call a black hole. So black holes can therefore be seen as huge particles or quantum mechanical entities that have mass but not matter. Additionally, universal expansion can't move matter, although it can randomly move subatomic particles. Therefore, there can be an interaction between black holes and our universe. As for gravity, it's a property of space around masses. Now, black holes do have mass, the same mass as the supernova core from which it formed. But the core was composed of plasma containing an equal amount of electrons and protons. Therefore, it couldn't have been charged. So why would a black hole have a charge? Apart from the fact that charge inside a black hole is a meaningless concept. As for black holes having angular momentum, I'll deal with it starting on slide 59. As for the event horizon, it's defined not as a physical thing, but as the border or edge where the black hole ends and space begins. From my perspective, it's the location where a black hole's high energy dark matter density drops enough for universal expansion to start creating spacetime. The picture can be a visualization as to a negative of space density around a black hole or a representation of gravity around a black hole. Scientists believe that a black hole's salient feature is its immense gravity. In other words, as we approach a black hole, gravity strength increases. That's normal. But inside the event horizon, they believe that the strength of gravity soars, becoming infinite at the center. That point, the center, is called singularity. But maybe inside the event horizon, gravity or the acceleration of gravity is zero. Remember, we can't differentiate between gravity and the acceleration of gravity. So let's explore the possibility that inside the black hole, gravity drops to zero. This graph shows the acceleration of gravity in and around the Earth. As we approach the Earth from space, the strength of gravity increases, but at the surface, there's a discontinuity, and below the surface, gravity drops. Since the Earth is not homogeneous, the line zigzags, but if the Earth's interior was homogeneous, the line would resemble the dotted line, and I'll refer to the straight line. The dotted line from now on. At the Earth's center, gravity drops to zero. Stay with me. Let's say, for argument's sake, we were to shrink the Earth's radius, but not change the Earth's mass. In this case, the rising section of the line would increase its slope. When the line reaches the new surface, the downward slope will still be there, but its steepness will also increase. And at the Earth's surface, the center, gravity will still be zero. If we could somehow continue shrinking the Earth, the slope on both sides of the surface would increase. Bringing the Earth's radius down to 134 meters, gravity would pressure the electrons and protons in the Earth together and combine them to create a neutron Earth. As you can see, in the neutron Earth, the graph's steepness would increase in both directions, but it would not be perpendicular to the x-axis. And at the center of the neutron Earth, gravity acceleration will still be zero. If we continue compressing this neutron Earth, obviously this is impossible, the radius may keep on shrinking and the graph will continue getting steeper, but gravity in the center will still remain at zero. If we couldn't magically compress the Earth until it became a black hole Earth would have a radius of 1/3 of an inch, the size of a marble, a black marble. But at the center of the black hole Earth, gravity must still be zero. Question: how about gravity inside stellar-sized black holes? Would this graph also apply to real black holes? For that answer, let's look at how gravity and time relate to each other in and around the Earth. The top graph I already explained. The bottom graph shows how time changes as we approach the Earth and continue going underground. You'll notice that in these graphs, gravity and time diverge. In other words, approaching the Earth, gravity accelerates, but time slows down. Below the Earth's surface, both lines seem to run parallel with time, appearing to shift upwards, especially as time approaches Earth's center. It would appear that as we approach the Earth, the progression of time, the green line in the graph, slows down. In other words, time slows down and seems to level off, maybe even reverse. Of course, we place clocks in space, but never below the Earth's surface, so the graph is theoretical. Clearly, at the Earth's surface, there's a discontinuity, but it's not the surface that's creating it. The question now becomes, does a black hole have an equivalent surface, a point where there's a discontinuity? In this slide, you see two graphs. The top one represents the acceleration of gravity, and the bottom one represents the time dilation caused by the black hole in our galaxy. The scale is off, but the concept I'm trying to explain is still valid. If we overlap the two graphs, they will cross at some point, and when they intersect, is the equivalent of the Earth's surface, meaning at this point, gravity and time flip. The top graph shows discontinuity around the Earth, while the lower graph shows discontinuity around the black hole. Both graphs show that after the graph's high point, gravity strength should begin dropping. In the lower graph, the black hole is the dark circle, and the event horizon is the outer edge of the black hole. The event horizon is inside this discontinuity, and we know that at this event horizon, gravity and time drop to zero. By implication, inside the black hole, neither gravity nor time can exist, which means there's no such thing as a singularity. Space inside a black hole has a constant homogeneous density. An object falling through the Earth will experience a lower acceleration, but its velocity will still increase up to the Earth's center. Looking at the graph above, we could assume the acceleration is decreasing, but the velocity will still increase, although at a lesser rate. But that can't be the case. As we approach the event horizon, the strong gravity slows down time and shrinks distances, lengths. Since velocity is dependent on time and distances, as time slows down and distances decrease, velocity must decrease also. That slowing down of velocity isn't uniform. To an object crossing the surface, the high peak in the graph, the front of the object slows down more than the rear. This difference flattens the object. The closer to the event horizon, the flatter the object becomes until it becomes extremely thin and gently flutters onto the event horizon. I will return to this on slide 52. Let's take a look at universal expansion in time from a different perspective. In a previous slide, I stated my belief that matter is just dark matter and energy bound together. The link here is for a video explaining this. Regular matter concentrates dark matter around itself, meaning dark matter or space density is higher in and around all objects. With the instruments we have, we can only measure this concentration around stars and galaxies. That explains the galaxy rotation curve, Mercury's precession, and gravitational bending. The higher space density around matter limits the creation of space-time around objects. In other words, universal expansion can't stretch space around matter as easily, therefore it can't create space-time as easily. Space-time is what the universe creates to prevent space from being ripped apart by its expansion. With less space-time being created near objects, time creation slows down. Around black holes, space density is so high that time creation slows down to a stop. I will return to this perspective again. Indeed, relativity teaches us that as we approach a black hole, time slows down and at the event horizon, time crawls to a stop. But relativity also says that time is dependent on the observer. Take a look at the link on this slide for a presentation about a physical description of time, not as a time as a dimension. But regardless of perspective, acceleration and velocity are time dependent. Velocity is distance divided by time, and acceleration is velocity divided by time. So if time slows down to a stop at the event horizon, acceleration and velocity must also slow down to a stop. Additionally, since motion requires time, and at the event horizon time stops, reaching a black hole's event horizon becomes an impossibility, and nothing can cross a black hole. So what happens to objects in free fall toward a black hole? Scientists believe that because of the extreme gravity around a black hole, anything falling toward a black hole gets stretched into long filaments, a process they call spaghettification. By the way, not an Italian concept. If you believe Newtonian mechanics and gravity is a force that comes out of masses, Spaghettification is painful since it stretches you past the point of no return. If you believe relativity and gravity bend spacetime, you and spacetime stretch equally, therefore there can be no pain. So when you hear some scientists talk about how painful falling into a black hole is, ask them if they are talking about Newtonian mechanics or relativity. As a matter of fact, length contraction is an effect of relativistic speeds. Although this effect is dependent on frame of reference, would this squashing on a future astronaut be as painful as spaghettification? Actually, gravitational waves are compressing and stretching you right now. Do you feel any pain? Here's my explanation for gravity as an effect of universal expansion. The top and bottom dark areas in the picture are areas with large masses, meaning high space density. The center, the white area, has a lower space density. If an object is placed in the center of the white area and the white area expands equally in all directions, the object won't move. If the object is moved closer to one of the darker areas, the light area is expanding faster than the dark area, therefore the object gets pushed toward the darker area. From this perspective, gravity is not a pull that comes out of mass, nor is it bent spacetime caused by mass, but more like a kind of pressure space applies toward all masses wherever there's a space density difference. This space density difference being caused by universal expansion. I never heard an explanation as to how universal expansion affects gravity if gravity is bent spacetime. In this case of a black hole, for object approaching the black hole, the pressure gradient is extreme. As I pointed out in slide 46, this pressure difference inside the imaginary surface doesn't stretch object into spaghetti, it flattens them. And by the time an object reaches the event horizon, it becomes a pancake, the thickness of dark matter which gets smeared on the outside of the event horizon, enlarging the black hole itself. Here's a cheap way to visualize what happens when a black hole forms and what you would see if you were to fall into a black hole. Get a hairbrush and press on the center of the brush. The bristles end converge toward the center. Similarly, falling with your back toward a black hole that has no photon sphere around it, you will see the stars in front of you converge toward the center. As the stars converge toward the center, their light turns redder. Their wavelength is stretched, and a red light ring appears on the edge. The picture has blue rings since that's all I could find on the internet. The light ring is formed by starlight from behind the black hole. As the light ring shrinks, the stars inside it crowd together, or actually your field of view shrinks. Unlike the picture here, there's no outside to the contracting circle. The entire universe seems to shrink. When all the starlight is gathered into one point and emerges with the light ring, the dot fades away. You've reached the event horizon. Your mass is now spread around the entire black hole. Falling while facing toward a black hole, an astronaut would see a dark area surrounded by a ring of light. Stars around the ring seem to move toward the light ring. Everything appears progressively redder. The ring expands to fill the astronaut's view, then blinks out. You fall into a black hole, and your mass is not part of the black hole. Your energy is totally irrelevant to the black hole, but it adds to it. Question: do black holes spin? Just before the supernova explosion, the star's outer region came crashing onto the core. Conservation of angular momentum requires the core spin to increase its spin, leading to the assumption that black holes spin. Do black holes really spin? We don't really know, since we can't see the black hole. But time ends at the event horizon, and spinning motion requires time, how fast the object spinning per unit time. Without time, black holes can't spin, besides exactly what's spinning. But we have pictures of black holes which show proof of spin. Well, there's a concept in general relativity called frame dragging. It says that rotating astronomical bodies drag space around them. In 2004, NASA sent Gravity Probe B, a satellite in orbit, to measure how much the Earth drags space around it. We were actually able to measure frame dragging. Could the implosion of the supernova core drag space around it, making space spin? When looking at a black hole, are we seeing the black hole or rotating space carrying light and matter along? In some cases, the black hole may be spinning at nearly 90% light speed, or is the space around it that's spinning? Another concept that came out of relativity is the concept of gravitational bending. In a way, gravitational bending is similar to refraction, the bending of light as it goes from one medium to another. For example, as light goes from air into glass, it bends at the interface between the two media. This goes by difference in light velocity, and we assign a value to it, the ratio between the velocity of light in the media divided by the speed of light in space. And here's the kicker. The index of refraction for space around the Earth as compared to intergalactic space has a name. It's called stellar aberration. If light crosses through two different media, it will bend twice. If it crosses three media, it will bend three times. In each case, this bending happens on the surface of the various media, and the bending is toward normal in the denser media. If multiple media were nested together with increasing density from the center point, and each media was very thin, the bending of light would be a continuous bending. It would look as if light made a perfect circle. From this perspective, gravitational bending is caused by space becoming increasingly dense as we approach massive bodies. The changing space density, coupled to the direction in which space is spinning, causes distorted multiple images of objects behind massive bodies. Stephen Hawking came up with the idea that black holes can emit particles. This radiation is believed to reduce the mass and rotational energy of black holes, causing a black hole to evaporate. I believe this radiation is dependent on gravitational lensing and the frame dragging caused by the black hole's formation. As I explained before, light entering denser space slows down and bends because it's carried by universal expansion. Space close to a black hole barely spans, but it rotates. As light approaches a black hole and the space around it spins, light's path keeps bending. Very close to the event horizon, space circles the black hole in a perfectly circular orbit. Therefore, light gets trapped into a circular orbit. Trapped in a circular orbit, light can't escape that orbit. Therefore, the space between that area and the event horizon is dark, as seen from the outside. As additional light gets caught in that area, the energy concentration increases until some energy turns to particle-antiparticle pair. Again, space can't move matter. Therefore, a particle can separate from light and leave their orbit as Hawking's radiation. Of course, that radiation doesn't come from the black hole itself. The black hole doesn't lose any mass since it can't interact with the universe. Scientists are still debating whether properties such as spin, color, polarization, etc., these are called information, if this information is destroyed when a particle falls into a black hole. It is also assumed that in our universe, information cannot be destroyed. But if black holes cannot interact with our universe, the problem of information destruction doesn't exist, since the particles that reach the event horizon are no longer part of our universe. Some scientists see black holes as time portals. According to relativity, all stars bend space and dilate time. The supernova explosion condensed matter and gravity before the black hole is even created. Being formed after the supernova explosion, the black hole itself didn't contribute to these effects. Let me repeat. Universal expansion creates space, time, and gravity. Since space-time creation ends at the event horizon, space density is too high and universal expansion can't expand space if it's too dense, then black holes themselves cannot affect space, gravity, or the timeline. This makes time travel using black holes an impossibility. Lately, there's been some debate about the creation of black holes. The James Webb Space Telescope discovered a supermassive black hole that seemed to have formed 570 million years after the Big Bang. But scientists believe very massive black holes couldn't have formed that early in the universe. Could this problem be pointing to a clue as to the universe's shape? I visualize the entire universe as being the red portion of this picture. The Big Bang happened in the dark center and is now outside our universe. The thickness of the entire universe is the thickness of the red portion of the picture. And right now that thickness is about 13.7 billion light years. The visible universe is just a round scoop of the entire universe. And the visible universe has a diameter of 13.7 billion light years. The location where the Big Bang occurred has been outside the universe 13.7 billion years, which is the thickness of the visible universe. We have no data about the dark interior. The oldest supermassive black hole James Webb discovered is not from the beginning, but formed in the past 13.13 billion years. Assuming we're in the center of the visible universe, the actual location is irrelevant. An observer 570 million light years from the edge of the visible universe and equipped with a James Webb telescope pointed in our direction will see a young Sagittarius A star. To that individual, Sagittarius star is 570 million years old. If the circle represents the universe and you are on the top of the circle of the universe north pole with a sufficiently powerful telescope will be able to see the bottom of the universe in any direction you look. If you want to see where the arrow points, you can only look in one direction, the direction that's the shortest. If you try looking in the opposite direction, you will never see the point, since the distance from the point to the bottom point expands at the speed of light. Therefore, light from that point can never get to your telescope. To summarize the presentation, when large stars exhaust their fuel, they explode as supernovae. The explosion happens on the core surface, not in the core center. Therefore, a black hole mass is the mass of the supernovae core. The angular momentum of the imploding core drags space around itself, and what we photograph is matter and light caught in this frame dragging. The compression from the supernova explosion races toward the core center, destroying matter, but mass, as denser space, remains, therefore gravity remains. Energy from the star destruction combines with the condensed fabric of space, forming a semi-quantum mechanical entity we call a black hole. Approaching a black hole, gravity and time strengthen exponentially, but time falls exponentially also. When a black hole's time and gravity graph cross each other, gravity turns around and begins decreasing. At the event horizon, time and gravity end. Inside the event horizon, time, gravity, entropy, etc. can't exist, and space density is high but uniform. No singularity or information paradox can exist inside the black hole.